Yeah, so hello. I think you're going to see some of the same stuff that you saw on Monday, but David Caroli and myself actually figured that if you see it twice, you'll have got a greater chance of learning it. And I'll put a twist on it, of course, because I'll tell it in a different way to the way that David has done. So what I want to do is sort of move on from thinking just simply about models and to thinking about how you might actually understand the observed changes in the atmosphere or in the oceans, and in terms of their forcing. You know, so is the ocean temperatures that we see inside the at the surface of the Earth really just simply due to greenhouse gases, or is it due to aerosols or volcanic, or perhaps it's just all internal variability and it has nothing to do with man's influence? So these are the sorts of questions that I want to talk about in this talk. I thought I'd also kind of give you a little bit of a glimpse of why these things are important and why Margaret Thatcher and Ronald Reagan set up the Intergovernmental Panel for Climate Change, and tell you a little bit about that experience. And then I'll talk about actually what we mean by detecting and attributing to influences to humankind or other forcing. I'll point to some ocean indices that are actually changed in response to climate change. And then I'll tell you a little bit about how the oceans are changing in response to greenhouse gases, and also the things that are missing. So, if you like, we can't actually say that everything in the climate system has actually changed in response to rising greenhouse gases. There's some gaps, there's some failed kinds of understanding. Now, IPCC was invented, if you like, by Margaret Thatcher and Ronald Reagan. No, it was put up by someone else, but they agreed to it. And it became an intergovernmental report to keep out the non-governmental organisations. But actually that was a masterstroke, because what it means is that IPCC's been around since the late 1980s, delivering robust assessments of our understanding of the human influences on climate change. Now, just to sort of give you a sense of the sort of difficulties that come with thinking about climate change, this report is an attempt to condense up all of the climate story for policymakers. Okay, so if you think about a policymaker, actually they struggle to read 16 pages. That's how long the summary for policymakers is. So they need some people to help them out. And the scientists all come out of the woodwork and offer, basically for free, to do this research on behalf of policymakers. Now, I was involved in Chapter 10. Chapter 10 is actually all about detecting and attributing climate change from anthropogenic sources. This chapter has 15 lead authors. There are some review editors. Now, IPCC is a very transparent process. It's a little bit different from when you actually publish your first papers. This transparency is needed to make sure that everything that we do is addressing the reviewers' comments that have occurred over the last 3 years. So what we do is we have 3 rounds of review. Normal paper would have 1 round of review. You then resubmit the paper and accept it and go into the peer-reviewed literature. Here we actually have 3 reviews. Normal paper, when you publish, will have perhaps 30 to 40 comments, maybe 3 reviewers. We, depending on in the round, got somewhere between 700 to 2,200 at the end of it. So, and when you write back to the editor, you'll say, oh yeah, we fixed that and we changed these words. Actually, we have a spreadsheet and we have to respond to every comment. And that spreadsheet will become available publicly at the end of the, early next year, it will become available publicly. And there are communities out there that are a little sceptical around the idea of climate change, and they will scrutinise this and they will track it and they will actually do an analysis to figure out whether we really did respond to each of those rounds and each of the reviewers' comments appropriately. So this is a different scale of scrutiny compared to a single paper that you might publish in a scientific journal. Okay, so this level of scrutiny means we better get it right. We've got a lot to justify and a lot at stake. Just to give you a sense of the sort of undertaking, this is the email count that I had in each of these 3 years. And so at the end of 3 years, I've received and sent something like 10,000 emails. Now, the Working Group 1 report is actually one of 3 reports. So in the case of this report, there's actually 14 chapters. So this is just one chapter. Each has about 15 scientists, so you can quickly work out there's about 200 lead authors. And we have another category called contributing authors, and there's about another 800 of those. So just in this single one report, it's actually 500 pages long, there's about 1,000 people who've scrutinised the text one way or another, or had their expertise drawn in one way or another to actually come up with the assessments. So this is an enormous effort by the community to produce just 16 pages. And in September, we'll actually go off and we'll have a rather exciting 4 days where between 120 nations or thereabouts, we'll actually gavel down, line by line, sentence by sentence, the summary for policymakers, okay? So there's an enormous... So you can imagine a room of 113, 120 nations sitting out there with their delegates, and if they don't like a sentence, up goes their flag. It'll get translated into 4 languages. We will then have a bit of a discussion around that sentence. Once they agree, it gets gavelled down and you move on to the next. And if you don't get to the 16th page by day 4, it just goes onto the floor. So climate change goes basically, here are the observations, here's the detection and attribution, here's what the future is. So if we only get halfway through, no future will be discussed in the summary for policymakers. So there's high stakes in getting to the end of this document. But the good news is it gets used. It gets used by those countries because, if you think about it, the amount of literature we have in this chapter is 1,500 references. So if you calculate that over 14 chapters, about the same, maybe 1,000 in some of the others. You've got 15 to 20,000 different independent articles. No one can read that many papers, okay? So you really do have to summarise it up and credibly put it together. And that's why this Nobel laureate says it's a remarkable example of mobilising expert analysis to inform policymakers. Of course, Australians of the Year, Tim Flannery. Tim Flannery's another famous guy. Thinks they're a bit dull. And he has a point, actually. They can be a little bit dull, but they can also be an extraordinary example of collaboration in the climate space. So, just to think about science, we've just had Stephanie talk about the list of tasks you guys have got to solve in ocean modelling. It was a bit of a daunting task, actually, and I was just arguing that's only 2 or 3% of the science you need to solve ocean modelling. The other 97 is actually in the models currently, so it's not all bad, but for climate change and understanding human influence, this is sort of the historical narrative. So back in 1995, we had this kind of language. You know, the evidence suggests a discernible human influence, right? We can just see something in the global climate. So that's nearly 20 years ago. Back in 2001, not so long ago, most of you are alive, you know, we're getting really bold and strong, new and stronger evidence that there was warming over the last 50 years, and it was due to us, okay? And then in 2007, we really went over the top because we said most of the observed increase. Now, most of means actually 50% of the signal is due to humans. In the back of our minds, actually, it's much more than that. And we also say here, very likely. So that means, actually, this is the first time we've got something that says, got a likelihood attached to it. This means we're 90% sure. There's a 10% chance we're wrong, that 50% of the signal isn't due to humans. So that was a pretty strong statement. And, you know, we even got a little bit more cleverer, because not only were we talking about the global things, we started to talk about the local things. Discernible human influences in ocean warming, continental average temperatures, temperature extremes and wind patterns. So you can see that now we're tickling down to things that have a different scale and different components of the climate system which we have detectable influences. So this is still back in 2007, and I can't tell you anything about the fifth assessment report because it's all in confidence, but there could be a sentence that there could be a sentence that goes something like this, you know, from all of these lines of evidence, it's virtually certain. Now, virtually certain is 99% sure, 1% sure, 1% chance of a mistake. So we're getting a little bit more confident, if you like, that human influence has warmed the global system. So that's kind of the narrative. But understanding actually the sources of influence on the climate system is really at the heart of the entire climate change debate, right? So it's important stuff to be able to come to grips with. And of course, being scientists, we like to root this in scientific process. So what is the attribution process? And I think maybe David might have shown you a slide that's very similar to this one. So if you think about it, here's say a picture of the global average temperature change since the 1850s. You can see that temperature's been slowly rising from 0.5, you know, about, it's, I've forgotten the number, 0.78, 0.8 degrees since the 1850s, it's 0.6 degrees since 1950 to the present, okay? And the question is, it's all very well to have these wonderful observations that tell you the Earth's warmed, but you really have to have an understanding of what the reasons are. So we know that greenhouse gases have been rising, and we know that greenhouse gases trap heat at the surface of the Earth. And so a plausible hypothesis is it's just due to greenhouse gases. But of course, we're not doing a clean experiment, right? This is environmental science, it's the Earth, it's only one of those. And greenhouse gases, it isn't the only thing that humans emit. We also emit aerosols into the atmosphere, and the aerosols are a very significant forcing, and I'll show you that in a moment. Now, they're the two main human influences, but there are some natural ones as well that have changed the Earth as well. We've had the large Pinatubo volcanic eruption, and if you think back to when we had the Pinatubo eruption, there was the beautiful, beautiful sort of orange purple sunsets, and that was really the aerosols that have been put into the stratosphere, changing the radiation balance on the surface of the Earth and cooling the planet. So it's plausible that there are contributions from the volcanic, and of course, and this is often discussed by skeptics, there's possibilities that solar variability has actually altered the temperature of the Earth, and also discussed, and very legitimate part of the discussion is, as you saw the previous two speakers, and you will have heard from the previous days, there's a natural internal variations that occur in the Earth, and they also affect the climate system. Even in the absence of any changes in greenhouse gases, aerosols, the absence of any volcanic eruptions and solar forcing, the system itself will naturally exchange between the ocean and the atmosphere, and it will have its own internal variability. And that internal variability can occur on all time scales, from days to centuries to millennia, okay? So it is plausible that internal variability is part of that hypothesis as well. Okay. Now, Stephanie gave that marvellous talk in the last hour about, I'm going to need that club. Stephanie gave that marvellous talk about models and all the uncertainty that comes from the models. So if you think about it, what we have to do is take the known forcings and project it through the numerical models to actually get a pattern. And the question you might ask yourself, does that pattern actually look like the observed changes in, say, temperature, or in in temperature or in the or any other field that you're interested in. So that is the nub of the question to do with the attribution process. So it's really the distillation of the scientific process. You're checking out the hypotheses around what is really driving this system, comparing it through the projections of the models, which you need, obviously, with the observations themselves. And you need a framework for doing that. So let me just take one step back. There are many possible causes of forcing, but unfortunately those forcings aren't well known. We'd love them to be perfectly well known, okay? I like that. Okay, so there are some contributions from greenhouse gases. Obviously the main driver in this figure, this is telling you the radiative forcing, the driver of change, calculated watts per metre squared by the main forcing. So here is the main greenhouse gases, CO2 is the biggest. But down here you can see that actually land use is a bit of a cooling on average, and the aerosols that come from pollution emitted by man are also a really big negative in the system, right? So what we have is things that are causing it to warm, positive forcing, and things that are causing it to cool, negative forcing. And we could have conspired on this earth to do both at the same time, okay? It's not a clean experiment anymore. It's not the way you would like to do the science in the lab. What you'd really like to do is just drive it with CO2 alone and drive it with the aerosols in themselves, by themselves. And really, if you look at this figure, you can see that in terms of this forcing terms from the known changes in the gases, so this is 1750, you can see that the greenhouse gas has a really narrow probability distribution. But because of our relatively poor understanding of the emissions of aerosols and the spatial distribution and temporal history of those aerosols over this entire period, we actually have a very wide distribution. And really it's the sum of these contributions that make up the total radiative forcing. And so this narrow, relatively well-known forcing is kind of slightly confounded by the more wide, much less certain forcing that comes from the aerosols in the atmosphere. And the combined response has this wide distribution. So there's a lot of uncertainty to do with even the forcing that goes into these models. So we need to develop a framework. We've got to have a means to take the projections of the models for the exact periods, roughly the exact periods, and to compare with the observations themselves. So we're just following the scientific method, if you like. And what we can do is we project, so this is the model projection of the type that's a coupled GCM in this case. And here is the surface temperature field that you might have for each of these periods from the past to the present. And you might call this X the state space for the model. And then you would take the observations, and the observations are imperfect because the battery's going flat. No, they're imperfect because we didn't really make lots of measurements of surface temperature in the Southern Ocean. We skipped out in the Arctic as well, and over the land we can't get them to report the temperatures. So the data has an imperfect coverage. And that coverage actually changes with time. So what we do is we compare the observations like for like. So we mask out the same gaps in the models as compared with the observations themselves. And really, what we're really asking is, these masked observations, how do they look like the model projections with the appropriate forcing? Whether it's just rising greenhouse gas or the aerosols or the combination of all of those. And we simply ask ourselves, well, this is actually much easier than making the models, right? Stephanie gave you a long discussion on how hard it is to make the model. This is the easy step, because all we have to do is compare the observations, y equals x, the state of the model, times a scaling coefficient plus some sort of understanding of the errors. That looks really easy, doesn't it? We can all do that, and you're absolutely right, because if there was only greenhouse gases here, we'd only be solving for a scalar here. The real problem lies here in the regression against the errors, the unknown part of the model. And the good thing is that we, of course, can estimate the scaling through total least squares or least squares. You come up with a scale, an estimate of the scaling. You can estimate the residuals, and then you can compare it with our knowledge of the uncertainty around the models themselves. And really, the challenge here is that we just want to understand the projection of the model with its uncertainty itself. We've got to understand a little bit about the structural error. Now, Stephanie in the last talk showed you some of the structural error, and a lot of the structural error isn't just from the models themselves, but it's actually also from the forcings which are uncertain by themselves, and also the way the model space is sampled, taking into account the sparsity of the observations themselves. The scaling factor here, and the way we've posed this, gives us evidence. So if the scaling was 1, this would say that the model state is actually a perfect replica of the observed state. Actually, this almost never happens, and I'll explain why in a minute. The last bit is really around the observations themselves, the internal variability. Remember that the climate system has its own internal variability, and that internal variability can actually be really big on smaller scales. And so it's this misfit that is the key part to understanding the relationship between the observations and our efforts at the modelling. And so unlike most of the least squares problems that you'll ever tackle in your life, there is very little that you need to actually know about this thing. It's all about the uncertainty around the internal variability of the models, the observational errors, and the structural errors that occur in the models themselves. So all the uncertainty is actually over here, it's not here. So that's atypical to the sorts of least squares problems that you might be familiar with. Now, if you think linear algebra is tough, let me just show you how to do this in a graphical way. And I have to actually thank my colleague, Miles Allen, for actually creating this slideshow. And I'm going to be a little bit mischievous. This is how you do detection and attribution graphically, okay? So here's the temperature time series. I have to go fast. Here it is against time. Here's the observations. And if we had a numerical model that included both natural warming and human-induced effects. So human-induced here means greenhouse gases plus aerosols. The model natural warming means solar variations plus volcanic, okay? They're really just the two hypotheses that every skeptic around climate change will hammer you on. They're the only two things that we really have to think about. Okay, here is the volcanic eruptions causing, in this model simulation, causing the planet to cool. There's also some solar variation in there, and the orange line is the greenhouse gases plus the aerosols. And the question you could ask yourself is actually the total response, the observed response here shown as dots, is really the sum of this plus that. And have we got it right? And, you know, is it too small? So we've underestimated in the models. Is it too high? So what is the correct answer? How much can we attribute to the human influenced factors, and how much can we attribute to the natural, and how much can we actually use that information to project into the future? Okay, so now I'm just going to play around with this figure here, and I'm going to flip through an enormous number of slides, but what you'll see is we've got here is the human-induced warming, which is just due to rising greenhouse gases and aerosols on this axis, okay? And so really we're looking at the orange line, and here is now the dates. And what we're going to do is make this curve linear in the warming. So we're now looking at the observed warming versus the human-induced warming, but we're going to transform this axis so that it becomes linear, okay? So now that human-induced warming is linear, so this should be a very straight line, which it is, and actually, surprisingly, the observations pretty much sit on it, okay? Now, we haven't got every part of the problem solved because we need to think about the natural factors at the same time. So if you think about it, we've really got two unknown things. We've got an axis around the human-induced warming due to greenhouse gases plus aerosols, and we've got another axis which is really about the volcanic influence plus solar variation. So we need to introduce another axis. So this is the natural variability. This is the natural warming here on this axis, and you can see the correlation of this with the human-induced warming. And the way to really look at it, and we're not looking at this with observations, but if we just flick through a few of these, just have a bit of fun here, you know, I'm going to break every rule about presenting something with clarity. You can see that there's a plane, actually. So here we have the human-induced warming, here we have the natural warming, and here on the third axis is the observations, and you've got some dates here. And we can keep going, and what we're really doing in this regression is creating the best fit line, best fit plane for the human-induced warming or the natural warming. And we can continue on, and it actually fits into that surface, and we find, if we switch back to plotting against time rather than against variables, the least squares best fit answer to the temperature field. So here was the original computations. What we find is when we scale it, so this is by the beta, that it's slightly lower, and that we've also reduced the anthropogenic component at the same time. And we frame or term this difference here as the human-induced warming that came from the best fit combination of the natural forcing and the human-induced components. I've forgotten what the question mark's about, but but if you think about it, what we've done is really we've tested each of those models, made sure that they now naturally fit the observations. Now you might ask yourself, why don't the models fit the observations? Well, it's a bloody good question, actually. But the reason is that when you operate the model, you take the known forcings, you then put them through all of the physics that's associated with the model, both atmosphere and oceans, and those errors propagate through. So it means that actually, even if you had perfect knowledge of the inputs, you would have uncertainty in the surface temperature field, or the ocean heat content, or the distribution of sea surface, sea ice, or upper atmosphere temperatures, because the models themselves have error, but also because the inputs have error, right? So we're pushing the errors through. So if you think about this figure here, this figure sums up everything. Here we have the scaling on, this is the human-induced warming, and in this axis we have the natural warming. Now this cluster here is created from the control run with no change. So what you can see is that the way to interpret this result here, this is the best optimally fitted combination of the human-induced warming plus the natural forcing, and you can see that basically the scaling of 1 to 1 would be perfect, and it would sit there. We've had to reduce the scale slightly to get the best fit to the observations. You can see that the natural warming is almost encloses on 1, and on this axis the human-induced warming sits nicely and straddles the variable 1, and the confidence interval is well separated from our understanding of the internal variability of the system. So in this case, you would say that you've detected and you can attribute a certain amount to human-induced warming and a certain amount to the natural forcings. And it's this kind of fit to the observations that, oops, got to change talks. And it's this fit to the observations that allows you to go to this figure here, which becomes the attributable component that's due to greenhouse gases, and here is the attributable component that's due to aerosols, And here is, in blue, is the attributable component that's due to natural forcing. So the last example had 2 variables. We were searching for a plane. Here we've got 3 variables. We're searching for a hyperplane. This is the best or optimal least squares fit of a complicated experiment that man has been doing on the Earth's atmosphere and oceans. And what we find is that the greenhouse gases is indeed the much larger forcing, but there is a negative contribution from the aerosols. So we've got warming, we've got a cooling by the aerosols, and natural forcings turns out also to be negative. And so if you take the contribution, the sum of greenhouse gases plus aerosols plus natural forcing, you see the observed change of just under 0.5 degrees for this 1950 through to 1999 period. And it's this kind of analysis that allows us to say it's humans who've done that, and the sum of those two is nearly everything, which sums up to that 0.5 degrees. And the only bit that we can actually attribute to volcanic eruptions and solar forcing is this small 0.2 degree cooling pattern here. But not all models are the same, and so you do it over a range of models, and you can come up with the attributable forces due to greenhouse gases, due to the aerosols that we're also emitting into the atmosphere, and there's a very weak contribution from the natural forces, including solar. And it's this analysis that actually allows the chapter on detection and attribution to say things like, it's very likely that greenhouse gases have caused most of the warming since 1950. Now, the oceans are changing too, and in the absence of, in the presence of just observations, we'd have a very simple state. The oceans have warmed. It turns out that that warming is a really important part of the total energy budget of the Earth. Here is the total heat that's been taken up by the Earth since, I've forgotten the period there, that must be 1993 to the present, and this must be the 1960s to the present. And what you can see is that this is the heat content, so the purple is for the old period, and then for all of the other known components of the Earth system, you can see their contributions to the amount of stored energy. And they're relatively small. Okay, the next biggest one is in fact the heat that's stored in the solid Earth in the continents. The atmosphere itself, unlike the oceans, doesn't really store much energy in it at all. Okay, and so if you sum up all these components, what we found in the 4th assessment report was basically that more than 80%, but we could actually say 90% of the total energy taken up by the Earth system in the last 50 years is actually stored in the oceans. So the oceans are a really critical component of the energy balance of the whole Earth. The atmosphere, if it was an atmosphere versus oceans thing, the atmosphere is a pretty unimportant element. That's not true. It does a lot of the transport. And the ice sheets, you might be surprised, is that the melt of the ice sheets, the glaciers and ice caps, is actually only 1% of the total energy budget. So whilst ice sheets are really important to sea level, at the time of 2007 that was 40% of sea level, they're actually only a small part of the energy budget. So the oceans are really important to understanding and climate change. And this figure allows you to think about what that time history is of the total energy content, this is heat content, taken up by the oceans from the 1960s, 1970s, let's say, through to nearly 2000. The black line is actually the observations, okay? And what we've put in here is just to illustrate it's the optical depth change from the major eruptions, Agum, Chichon, Pinatubo. And you can see, even in the ocean heat content, there are variations in the ocean heat content which tend to coincide with these major eruptions, Chichon and Pinatubo in particular. And laced on this figure is actually what the various models tell us when they include those volcanic eruptions and the known greenhouse gases and aerosols. And you can see that there's a wide divergence between the models. For example, that one. There's a wide divergence between the models, but they tend to have very similar patterns of rising ocean heat content and a tendency to, with the volcanic eruptions, to have a nice cooling period immediately after the eruption itself. So this is a good sign that both the models and the observations, they're totally independent, are actually in relatively good agreement. And this figure, which has only now came out in 2007, gives us a lot of confidence that they're beginning to both model the oceans and the drivers of change relatively accurately. Just recently, we've been thinking about how to actually test the emergence of human influence in the ocean system. So this is sort of a slightly complicated paper, but the key element is this concept here of signal, so that's the change in ocean heat content, to noise. Noise being, of course, our understanding of the internal variability that comes from models, actually. We only have one planet, right? So how do you estimate the noise when you've got constant greenhouse gases? Actually, you depend on a model to give you that answer. And so we use the models to estimate the noise, because that is the best source of estimates for noise of the Earth system. And the signal-to-noise ratio is here. And what we've done is we've just looked at a linear change in ocean heat content over the last, well, it starts in 1970, so the last 15 years, the last 20 years, from 1970 to 1995, 25 years to 30 years, 35 years. And what you can see is, I figured out most of the curves, just think about sort of the average one through there. And what you can see is that we exceed the 1% significance level after 15 years of record. And by 20 years of record, it's still going up. And by 30 years of record, we're well and truly above that 1% level. And so what that really means is that if we had a good understanding of the observations and what we were doing and the numerical models, in hindsight, we could have said we were virtually certain in 1985 that there was a detectable human influence on the climate system. In 1985, we could have said that. That's before the first report that came out in 1990. Unfortunately, we weren't quite in that state, and so we're actually staying in 2013. So science is a little bit behind in the sense of analysis of the data. This morning, Paul Spence talked about ocean temperature and ocean salinity. And he talked a little bit about how ocean salinity was set in the various different oceans. It turns out that ocean salinity is also changing in the ocean interior. There's a thing called the shallow salinity maximum. It's characterised by a high salinity that decreases with it's a maximum salinity, and it's mostly formed in waters that are in here, in the evaporative cells of the global oceans, similarly in the northern hemisphere and also in the Atlantic. You find it about 200 to 300 metres below the ocean surface. This is the observations from old data. There's a few million profiles of salinity, so there's enough to actually consider a difference over a 30-year period. And what you can see is that the new data, indicated in red, have become more saline. So the waters that originate in the surface waters and sink into the ocean interior down to about 300 metres have tended to become more saline over the last 30 or 40 years. You can look at the waters that are actually formed at higher latitudes in the Southern Ocean and also in the higher latitudes of the Pacific and Atlantic and Pacific. And what we find there is a reverse story. So the surface waters are fresh, and there's a tendency actually for those surface waters to become, shown in the red here, to become progressively fresher as well. And I can show you, so this is really an amplification of the current salinity patterns that we see in the ocean interior. If we look in the models, we actually see exactly the same thing. So this is work by Stephanie Downs, and here you can see in modern times there's a tendency for the old waters to become lighter, so moving to the, and fresher at around this salinity minimum here. In all of the models, this is pretty much the same pattern. So, so what we're finding is that even in the models with all of their structural errors, a tendency for it to look like the observed changes of ocean salinity itself. And just recently we've had the nice work where the surface waters of the ocean have also been analysed in much more detail. And Paul Spence talked a little bit about how there was a high salinity in the Atlantic Ocean, and that high salinity was caused by the evaporation over the Atlantic. The easterlies carried that moisture. It rained into the Pacific and parts of the Indian Ocean. Now this is the mean salinity, so that was an explanation for this pattern here in the equatorial zone. But if you look at the 50-year trend of salinity change, what you see here is that most of the Atlantic has got saltier, so that's increased evaporation, and most of that equatorial zone has actually got fresher, particularly over here, over the Indonesian archipelago and the western part of the Pacific. Detection and attribution studies have been done on the surface salinity changes, comparing them with the models, and here you can see that scaling parameter. So the scaling parameter is telling us that the models are consistent with the observations. They're around 1, right? They get the scale, same scale. And they also tell us from the confidence intervals that are being shown here, which is the 90% confidence intervals, that if we work on the whole of the Pacific, so these results are for the whole of the tropical Pacific, that there is a significant salinity change that can be attributed to both greenhouse gases and aerosol forcing. If we work in some of the other basins, much more at a finer scale, you tend to see that these are not significant, i.e. they're not different from zero. The confidence interval overlaps. And so we can't actually distinguish those Atlantic signals. But there's a physical conclusion that goes with that. What Paul was describing was part of the moisture transport in the equatorial zone. And those results are telling us actually that there's an increased amount of transport of moisture from the Atlantic into the Pacific, making these waters fresher relative to the Atlantic itself. And so now we have a statement actually that there's an anthropogenic component forcing the changes in the distribution of rainfall over the surface of the Earth. And there's a lot more evidence that actually says that the ocean salinity is becoming one of the best rain gauges that we have for understanding precipitation change. Right. It turns out actually that over the terrestrial land system, the observations are not good enough to even attribute a human influence to it. So we have an interesting result here where something as abstract as ocean salinity is now starting to tell us something about that changing nature of rainfall over the surface of the Earth. So there's another really important indice that you might not think about at first. Someone asked about biological things being added to the ocean models this morning. Ocean oxygen is an example of a biologically driven variable, biologically and physically driven variable. And the question, there are many observations now that are showing that basically that the oxygen content of the ocean is decreasing. The surface of the ocean is normally saturated in oxygen because there are breaking waves, right? The ocean has always got breaking waves. It's always inserting bubbles into the top 100 metres into the mixed layer, and so that surface water is actually at 100% concentration. But with the circulation of the gyres, water sinks into the interior, and biology consumes the oxygen, and so the oxygen level naturally decreases within the ocean. And oxygen is used actually as a tracer of ocean circulation. But what we can do is we can actually also test in a very broad way whether oxygen has actually changed within the ocean and whether it's lowered. And that's what this figure is showing us. This is the zonal pattern of oxygen decline. Blue is a decrease, the yellows are positives, in the zonally averaged from the northern latitudes to the southern latitudes. And what you can see is that there's a lot of decrease, typically in the high latitudes, north of the middle of the subtropical gyres, and also in the polar regions in the southern hemisphere. We actually expect that there would be a decline in the oxygen concentration in the oceans, because we know that there is evidence that the amount of carbon that's being taken up by the oceans, the amount that's emitted carbon that goes into the atmosphere, the fraction of that is actually tending to decrease in the oceans. So we're suspicious, even in advance of doing this work, to understanding that there might be some oxygen changes. But the question you might ask yourself is it actually of anthropogenic origin? And so we've been, even in spite of the sparsity of the data set, we still mask all the observations to make sure that we compare the models with like for like. We do the same kind of regression analysis. And what you find is that if this is the internal variability here shown in this figure here, you can see the response of the observations, so that has an enhanced sort of change. And here is the numerically calculated ones that come from either the Hadley Centre Earth System model or from the Max Planck Institute Earth System model. And in both cases you can see there's a tendency for the high latitude areas to decline, and the mid latitudes and equatorial zone have the smallest changes. Now, some of you will say, oh, that's not particularly good, the model's no good and all that kind of stuff. Actually, that's a completely reasonable response. It turns out, though, that if you do the full analysis and you run it through the system, what you do find is the scaling factors here are not quite one would be here. So the model is underestimating the response observed in the oceans, but they're both significantly different from zero, right? So the model is unable to produce the full amplitude of the response, but as far as we can tell, comparing it with the internal variability that we understand that comes from the control models, that these are significant differences for all forcings. So that's both greenhouse gases and aerosols. So in that paper we came to the conclusion that it's very likely that the oxygen decreases have an anthropogenic component. And the other thing that we discovered, of course, was that the biology didn't really matter. It's all driven by the physics. Okay? So for some things, some parts of the problem simplify up into the things that you think. So let me conclude. It's completely clear the ocean is changing, and in fact our observations are good enough, even in 1985, before Argo, before the sophisticated new measurements, that actually there was a detectable influence from humankind, and that the strength of that signal is continuing to rise. We really need to include the volcanic forcing, and that's a very distinct part of the signal. The surface salinity, which is actually our best information we have around precipitation changes in the water cycle, does show an anthropogenic component, particularly in the equatorial zone. And also I showed ocean oxygen changes. So there's really an amass of evidence that's coming in the oceans for responses that we can attribute to human influences. And really what we're saying is it's driven by greenhouse gases and aerosols, and the models have a projection which does align with the observed changes. And you say, oh yeah, okay, so David Carolli talked about surface temperature last week. You've got these ocean ones. We've seen the sea ice in the Arctic decline rapidly. We've seen snow cover change in the northern hemisphere, and they all have attributable human influences. But are there parts that we have failed detections? So I think Stephanie ended her talk by saying the challenge for you guys was to do all that modelling work. Is Stephanie here? Well, Stephanie, I say, stuff that. This is where you guys got to be working, right? This is where we have failed detections of human influence. The Antarctic ice sheet has lost hundreds of gigatons of mass. Its melt is found over the Southern Ocean, but can we find a human influence in it? No. There's no ice sheet model that's really good enough to tell us about how it's changing in response to greenhouse gases. And so we just don't know. Just don't know. It's almost like Rumsfeld. And then if you think about Antarctic sea ice, we have exactly the same problem. Instead of Antarctic sea ice declining, it's actually increased 1.3%. Actually, it's undetectable because it's in the noise. But the Antarctic sea ice has not behaved the way we thought in response to rising greenhouse gas. Failed detection. And precipitation. Now, precipitation we've been measuring since the 1880s, and many people do it, but it's actually a tough variable. It's not a Gaussian, it's a Poisson distribution. It's very hard. We have mostly failed detection of human influence in precipitation, and we certainly have failed attributions. Tropical cyclones is another issue, and this is where you guys ought to be investing your time. Sorry, Stephanie. Thank you very much.
As a contributing lead author, what's your role in hammering out the details in those 4 days? Do you have to actually get out there and...
So, yeah, okay. So when we get to Sweden, my role will be to make sure that the government's... It's the government's reports, okay. So the countries own these reports. I don't own the report, nor does the other lead authors. So our task is to just make it true to the science. Okay. So of course people like yourself might think that those governments will want to alter the agenda and downweight the science, and they want to raise the political bandwagon. Actually, it doesn't happen, not for these reports. What happens is that there are many nations in the room, so even Saudi Arabia toes the line on what the science is, and in fact the interaction you get in the plenary sessions is that the text improves. The text actually improves, right? It doesn't get worse, it improves. So you might be surprised to hear that. And often they actually ask for extra figures. So there's a bunch of policymakers, right? They don't want a graph, do they? But actually ask for it. And so often there's another graph that's added. It's very restricted. There's quite a lot of discussion about some of the issues, and there are some really exciting moments in amongst. It's like fishing, right? It's really boring most of the time. But occasionally, one of the nations will resist a sentence or half a sentence, and remember, it spills on the floor if it all gets, or you go out to the room out the side and have a long discussion. But it gets negotiated on the fly, in plenary or just outside. You come back in, you resolve it. And typically I found actually that the science was preserved, right? What the governments were more interested in was just a coherent story. Might seem surprising, but that's actually what happened. It is 113 nations, what herding sheep is like. So I put this figure up just mischievously because this is actually showing all of the things for which there are detectable changes in the climate system, in addition to oxygen, ocean salinity and so on. And virtually everywhere you look, there's something that's caused by humankind, except in the Antarctic.
What is the consensus on the effect of the solar variations in the forcing? Is it a big part? I mean, the timescales are minor solar variability.
So I don't know why solar variability gets such a lot of airspace, to be honest. solar variability cannot not actually change the temperature of the Earth on average at all, right? Because the amount of sunshine that's landing on the surface of the Earth is pretty much fixed. But there are little variations, 11 years, and that's got a very distinct cycle to it. And because of the tilts of the Earth, you can, which vary over time, you can get regional regional changes driven by solar variability. But on the average of the temperature of the Earth, you can't. So if it's 0.6 degrees of observed change, solar variability is 0.02 plus or minus 0.02. Average is 0. So it's a tiny driver in that system, even though we can detect it regionally. Okay.
So usually the first response is that this isn't anthropogenic. It's you don't have the solar from the first
So exactly, and the graph that I can't show you shows that. Yes.
So the summary for policy makers has all the going attended by defendants with all the nations. But what about the other preferred, like the technical summary of the whole report? What kind of government input is in?
What kind of
government input, or is there?
The governments. So there's 3 review stages. The second stage is government plus science experts. So the governments get to review the document in the second order draft.
Okay.
So there's often the government experts are the same as the science experts, depending on the country, but the governments all read it. And anybody can read it actually. So, there are quite a few famous skeptics who've read the various chapters, make their points. So it's a bit more transparent. We know who they are and they know who we are, and it's all listed in there. It is open. It is open and it is transparent, but it is very thorough. Yeah.
You had a slide a couple of while back which showed detectable change with salinity, which helped to enhance the water circulation in the tropics.
Yes.
What are your thoughts on that in terms of future changes related to ENSO as a result? In the projections, what we see is that ocean salinity, where it's fresh, gets fresher, and where it's salty, gets saltier. So the water cycle itself is being amplified. And if you do the calculations relatively carefully, the ocean salinity gets amplified at about half the rate we expect per degree of temperature change. And the reason for that, so I'll kind of answer your question in a moment. So the reason for that is that as the ocean warms up, it gets a little bit more stratified, and so you actually retain the fresh water in the surface water. So in the case of the moisture transport between the Atlantic and the Pacific, we would expect that to ramp up too. So we would expect fresher over the Indonesian and more salty over the equatorial and other parts of the Atlantic. And that will go up at twice the rate that you'd expect from our system overall, so about 14%. Half due to the stratification and half due to more rain.